Welcome everyone for this VLS studies and lecture series. In today's lecture video, I'll be discussing about resettable latches and flip-flops. Mainly, there are two kinds of reset, which we are going to discuss in this particular topic. Synchronous reset and asynchronous reset. Asynchronous reset forces the output to low immediately, while synchronous reset waits for the clock signal. Synchronous reset signals must be stable for a setup and hold time around the clock edge, while asynchronous reset is characterized by a propagational delay from the reset to output. So let us first discuss about synchronous reset. Let us consider this particular circuit where an AND gate and a transmission gate as well as a tri-state buffer is used in synchronous reset. So we already know the truth table or how exactly a D latch works. When clock is high and suppose reset is 0, whatever is the value of D, here we have considered as 1, that will be reflected as output Q, which is 1. For example, if clock is 0 and reset is also 0, even if D input is 0, because clock is 0, the previous state will be retained as it is. That is 1 which was previously present, it will be retained as it is. So now let us discuss how this reset function is achieved. So when clock is high and reset is high, as well as D input is logic level 1, because reset is 1, Q will be forced to become 0. Let us verify this truth table, whatever we see here, with respect to the circuit which is observed here. Let us consider the first case. When clock is 1, reset is 0, and D input is logic level high, the output which we have to get is 1. Q should be equal to 1. Let us see how we get that. So when clock is 1, 5, clock is 1, clock bar should definitely be equal to 0. So clock bar is 0. And when clock is 1 and clock bar is 0, this transmission gate, whatever we see, is turned on. So when transmission gate is turned on, there is a connection established from this end of the transmission gate to this end of the transmission gate. It acts as a closed switch. Whereas when clock is high and clock bar is low, this tri-state buffer, whatever we see here, it will be off. So it acts as a open switch. There is no connection from this end to this end of this tri-state buffer. Now let us consider these conditions. So when reset is 0, reset bar should be equal to 1 and D is equal to 1. The input which we are given is 1. So 1 NAND with 1 is 0. We already know that. So because this transmission gate is turned on, it acts as a closed switch and the 0 will be transferred to this particular point. And 0 inversion is 1. So the output which we get is logic level high. So it satisfies the truth table which we have seen previously. Similarly, this 0 will also be inverted over here and it will be present over here. But because this entire tri-state buffer is open circuited, it cannot be transferred to this particular point. So this is the first case for our truth table. Next. Let us consider one more case. When clock is 0, reset is 0, and D input is also 0, Q output, whatever we have to get, should be 1, which is the previous value. Because when clock is 0, previous state should be retained as it is. Let us check that once. So when clock is 0, clock bar is high. So this clock 0 input is given to this NMOS transistor and clock bar 1 is given to this PMOS transistor. So this transmission gate is off. So if the transmission gate is off, it acts as a open switch. That is, there is no connection from this point to this point. Whereas when clock is 0 and clock bar is 1, this tri-state buffer is on. It acts as a closed switch. There is a connection between from this point to this point of the tri-state buffer. Now, let us consider the case now. When reset is 0. So when reset is 0, reset bar is 1 and D is 0. So I'll append the same thing. 1 NAND with 0 is 1. But this 1 cannot be transferred to this point because transmission gate is completely open circuited because of the clock signal which we have given. But previously, logic level 1 was already present over here. Previous case we have seen. So that logic level 1 will be inverted because it acts as a closed switch here and we have a bubble over here. This 1 will be inverted and will get 0 at the output of this tri-state buffer. And the same 0 will be transferred over here. 0 inversion is 1. So the previous value, whatever it was there, that will be retained as it is. So this is how it works. Similarly, let us consider a condition where reset is high. So when reset is 1, no matter whatever is the D input, the Q output should be equal to 0 because reset is 1. Let us consider that. When clock is high, clock bar is low. Clock high value is given to the NMOS transistor here. 0 is given to PMOS transistor. So this entire transmission gate is on, whereas this tri-state is off. So if tri-state is off, it acts as a open switch. So because reset is 1, reset bar is 0, D input is 1. So I'll append it over here. 0 NAND with 1 is 1. Because transmission gate is on, 1 logic level high which is present here will be transferred to the other side of the transmission gate. So 1 inversion is 0. So when reset is 1 or reset is triggered, whatever might be the D input, the Q output becomes equal to 0. So this is how resettable latches, and in similar way flip-flops also work. I hope that you have understood this video lecture. Thank you.